Okay, so on the first video, I just give a brief introduction on set theory. So we start with set theory using this book, Real Variables with Basic Metric Space Topology, and we start with basic terminology. So at this point, we know what is a union between sets. We know what is an intersection between sets, and also what is a complement. Okay, and on this video, as on the last video, we finished solving a problem from this first section. So this was the first problem that we solved. So it was basic, based on an arbitrary collection of sets. We we have to prove using De Morgan's law that these equations they are true. And remember, this I it means a collection, an arbitrary collection of sets. So we can read this as a intersection of an arbitrary collection of sets A. And this C is a complement of this set, of this collection of sets. And this is the method, the notation that we use to represent a large number of sets. Okay, so this was the problem 1 of this section. And on this video we will solve also the problem 2. So just let me put this a bit down just to create some more space right here. Okay, problems. For section 1.1. So these are two different equations. One for represent an arbitrary collection intersection of a collection of sets, and this one an arbitrary um, collection of union of sets. And we need to prove that is true. So with the given equations, prove that they are true. Using De Morgan's law. Okay, so if you watch the first video, so you know how to solve this. And now the problem number two asks to us to prove okay right here I wrote wrong. Sorry. Let's prove. So prove that union distributes over intersection. Okay, okay, so A in a union with the intersection between the sets B and C. So applying the distributive law, we know that the distributive property, we can rewrite this as a union between the sets B, A and B in an intersection with the union between the sets A and C. Okay, this book is very nice because it becomes with the solutions. So again, if you got the opportunity or if you find this book online, is real variables with basic metric space topology, which is from this author Robert B. S. So I got the solutions, but also instead of only use the solutions, it is good for us if we explore different ways, different approach to solve the problems. And the basic theory of sets is very simple. So remember that we can use Venn diagram to solve problems with a smaller number of sets. So right here we are dealing only with 3 sets. So it's about set A, B, and C, and it's not a collection of sets. So when we are dealing with a collection of sets, we use this notation. And before I start with the solution, let's recall some ways to represent these equations using the Venn diagram. So if you remember, so this will be a briefly recall. So this will be good to us to understand uh, more deeply about this problem. So let's recall something. So first, if we have a set A in a union of set B, so how we can represent this using Venn diagram? Well, this is very simple. Okay, so represent using Venn diagram. Representation with Venn diagram. Okay, this is very simple. A set A in a union of a set B with a set B. And we have to fill it all the two sets this way. So this is a diagram representation. And let's say we got a element x. So if we got, for example, an element x, let's say this element x we are representing right here on the set A, but as the set A is in a union with the set B, so x belongs not only to A but also x belongs to the set B. And let's say if we represent this element x on the set B, so this element x not only belongs to the set B, but also it belongs to the set A, because again they are in a union. And representing this element right on the intersection between the sets, so we can write that x belongs both to B and A. Okay, and now what about intersection? So now again is about two sets, A and B, and okay, so is an intersection A in intersection with the set B, and the Venn diagram of this representation is this way. We have to fill it the region of intersection between the sets. And now let's say again that we got a element x, and now let's place this element on the set A. So x belongs to the set A, but x does not belong to the set B. And x, as you can see using this Venn diagram representation, we only have the element x on the set A, not only on the set, not on the set B. On the set B, we do not have this element. But still, we can tell that x belongs to the intersection between the set A and the set B, which is different of x B on the set B belongs to the set B. So this is different. We cannot tell that the element x is on the set B. This is not true. But if we put this element right here now on the set B. Now having x on the set B, we can tell that x belongs to the set B, but x does not belong to the set A. And still we can write that x belongs to the intersection between the sets A and B. Okay, so we are remember this. We do this recall because before I use the solution of the book, which is from my point of view, or since I know a analysis of this equation. To understand what is being said, I wanted to write uh, the Venn. I wanted to draw the Venn diagram of this equation. Okay, so let's do it. In this recall, now you see that will be useful for, so we can do this. Okay, so as this is an equation, what is on the left side is the same as on the right side, so it's only write it in a different way. So let's try draw this diagram, this Venn diagram, using the both sides, and it needs to be the same. It has to be the same. So okay, so these are three sets, and what is easy to do first? Okay, is B in an intersection with the set C. So this is easy to us to do. So the set B and the set C in an intersection. Okay, so that was easy. And what is left is the set A. So the set A is in a union with the intersection between the sets B and C. Now, if you find it difficult doing this, let's use the right sides of the equation. So this is will help us. So we can see right here that A is in a union with the set B. So this is a union. Okay, so let me try different. Let's say now using only the right side of the equation. So the set A is in a union with the set B. So let's fill it or shade all this region completely of the set B and A. And also for this union between the set A and C. So the set C, let's fill it out this region with the set A. And this way, this region um, is left empty. We are not filling this region. Okay, I'm not so sure about this solution using Venn diagram, but now using the solution of the book, which is again, from my point of view, since what I know about this subject is more a analysis of this equation, and we can try to verify this solution using the solution of the book. So let's see. And it says that if a element x belongs to a union of the set A between the intersection of the sets B and C, then either x belongs to A or x belongs to B in intersection with C. Okay, so let's try to verify this using the Venn diagram. So if we again place a element x, let's say the set A, but the point is where we place this element x based on this notation, this description. A set A in intersection with, sorry, right here is a union. So where we place this element x on a set A in a union with the intersection between the sets B and C. Well, if we look at these partitions, if we can call it this way, because is this A and is this intersection. So if you look at it, we can see where we can place this element x. So x belongs to A, something like that, and x also belongs to the intersection between the sets B and C. So something like that right here. This is the intersection between the sets B and C. So maybe we can place the element x right here. Okay, and it keeps going saying that in either case, X belongs to a union between the sets A and B in an intersection with the sets with the union between the set A and C. Well, this is more complex to verify, but we can give a try. Okay, so let me copy this and let's try to verify what is being assumed right here. Okay, so X belongs to a union between the sets A and B, so we can say that X is an element that belongs to the set B or the set A, and also X belongs to, well, I think right here with this intersection, what is being a look that we need to have is something like a reverse, not a reverse, a inverse look, like let's say a union A in a union with C, and because of this intersection, this turn it into a inverse. So instead of X be on the sets, because of this intersection, it will be on this region. So we have to pay attention to this, because just because of this intersection, the way that the element will appear on the sets, it got inverse. It becomes inverse. So I think we can do better. So is A in a union with B? So the X elements will appear right here, and A in a union with C. And if you can notice, we do not have B in a union with C. Okay, so right here, probably the X element is not right here. So again, as this is in an intersection, instead of we place the element X right here, this intersection, it will kind of inverse the way that the X appear on the sets. So again, we can conclude that X is right here, because is A in a union with B and A in a union with C, and an intersection between the union of the sets. So right here, I hope you can see this. Hope you can understand what I'm trying to explain to you. Okay, and still keep saying that conversely, let X belongs to an intersection between the union of the sets A and B and a union of the sets A and C. So if X belongs to A, then X belongs to a union of the set A with the intersection of the sets B and C. Assuming that X does not belong to the set A, then X belongs to the set B and X belongs to the set C. So X belongs to a union between the set A in intersection with the set B and C. And as I said, from my point of view, since what I know, this solution is a kind of a analysis, and we have proved this using the Venn diagram and these first assumptions. Okay, and this way we conclude the second video, and hope you understand what I tried to hope you understood what I tried to explain to you. Also hope you hope you enjoy, and we will keep going solving some problems of this first section on the incoming videos. And for now, that's all. Thank you.